As a solution architect, I'm involved in our LPWA activities at DT since basically since the beginning. So since we rolled out NB-IoT in 2017 and sometime later LTE-M. And during that time, I've seen a lot of solutions, and it's amazing on what kind of performance customers can reach or achieve with the new power saving features which these new rod types have to offer. However, it's also sometimes sad to see what kind of potential is wasted, as not all of these features have been understood or applied correctly. And for this reason, we now try to introduce or have a closer look on which features are available and how they work. So in the old days, we usually were, this was basically the pattern which we have seen everywhere. So this is what was done with 2G and GSM, so all the time. So whenever a module wanted to send data, or if you want to have a battery efficient solution, then you would just turn on the module just before you want to transmit data. Then module would then perform network acquisition scan, perform attach procedure. And then after this, you would send the data. And shortly after this, you would turn off the module. So this was considered the most efficient way to operate a module when it comes to battery lifetime. However, there are a lot of problems with that. So these network acquisition scan can, with these new technologies like NB-IoT, take quite some time. So by this, burn a lot of energy. And also the attachment by itself also takes some energy, as error messages are exchanged in this. So in general, it's also not good for the network, as puts a lot of stress on the network. There's a lot of signaling involved during the attachment procedures, and for this reason, we try to get rid of this. And when we look at this in closer mode, then 3GPP has introduced a lot of features for this. But to understand these features, it's a good idea to first have a look on the RRC connection or on the connected mode or idle mode, as they are called. So these are two modes which are on the highest level of the, let's say, of the protocol stack when it comes to the error messages, which are exchanged between the eNode B and the base station and the terminal. And you just have to consider two of these modes which are connected and idle. So from the RRC protocol. So RRC is for radio resource control, and it's basically an indicator whether you have an active session with the base station or not. So, and what's important to understand is that you can only transmit data when you have an active session on the base station. In other words, when you're in RRC connected mode. So, and this is what the module does all the time. So when we look on this slide, so there we can see it pretty easy. So a module wakes up, for instance, from a power saving state or from idle mode. Then it will do a short scan to find the cell again, so to find the base station again. Then it will perform a random access procedure. For this, it will transmit some data, burn some energy. Then you would usually transmit the data you have to do whatever you want to do, so to send telemetry data. And all this is only possible in connected mode, so sending data. After this, a timer kicks in, so the RRC inactivity timer, and the module will then stay into this connected mode until this timer has expired. And so as at this stage, at any point data could arrive, the module has to constantly monitor the downlink control channel to see if there's incoming data. And for this reason, we can see here that we have a constant level of, or more or less constant level of power consumed as the receiver is on. When the timer is expired, so no data has been transmitted, then the radio resource control is released. So for this, a short message is exchanged with the base station. And after this, we drop into idle mode. It's important to understand that we have basically just these two features. So just connected mode and idle mode, and all the power saving features can be aligned to one of these two modes. So let's start with power saving features for the connected mode. So the first thing we have here is connected mode discontinued reception, and discontinued reception is usually abbreviated with eDRX. So, and in this mode, we then have we just do data. So here would be random access, data transmission. During this period, when we are on RC connected mode, then we do not have a constant, the receiver is not turned on constantly anymore, but it's pulsed like in the idle mode. So for this is just because there's an understanding between the network and the module and at which interval downlink data can arrive. And the receiver can be turned off in between. So this is some feature which also already helps you to save power. When it comes to this feature, it's important to remember that the operator has to support it and the operator has to turn it on. So there's no way to just make a module use connected mode DRX to save power, but the operator has to offer it. When the module also supports it, then the module can profit from this feature. Yeah. We can then again see it here in the power trace. So this was taken in our network, and as you can see here, so the interval, the DRX interval between these single let's say pagings is the same as for the iDRX mode. Yeah, and just by having the the receiver not turned on constantly, we can save a lot. We can save a lot of power, as seen on this slide. So where we have just a comparison of these two measurements, you can see for what long amount of time we do not have any power consumption here. Okay, that's the first connected mode power saving features. Especially when this one is not deployed, then it's a good idea to look at release assist indication. So release assist indication is a feature which allows you to shorten the time you spend in connected mode. So whenever you have sent data again, so like here, then you can tag in the message you're sending that you want to use release assist indication. And by this, you would then skip the following connected mode. So you would not have to wait for the inactivity timer before you drop into idle. And by this, have to pay for this this amount of time, this energy. But you would shorten the RRC connected mode and drop into idle immediately. Yeah. So you can see what this means in this mode. So here data has been sent, release assist indication kicks in. And although normally you would have to spend the time in this red box still in connected mode, we are now already in idle. This feature comes in two flavors. So this means we can either cut the connection after the uplink package we are just about to send, or after one downlink package which comes afterwards. So that's important to know because this can be easily misused. And in this case, you would then build up an anti-pattern. So to see what I mean, we have this slide. So above here's the situation without any release assist indication. So in this, I would send some uplink data, consume power during the transmission, then stay into RRC connected mode. At some point in time, the downlink data would be received by the module. And after this, we would then wait for the RRC activity timer to expire. And when it has been expired, then we would an RRC release would take place and we would drop into idle mode. With early release indication, we would send uplink data, indicate that we wait for one more downlink package. So after this, we go into a connected mode until we receive that package. Then immediately have the release from RRC connected mode and drop into idle. If we just indicate that we want to release immediately so that the RRC connection would be dropped, should be dropped immediately, then we would send uplink data, release the connection, go for some pagings into idle mode, be paged by the network, then the module would have to go through the whole process of setting up an RRC connection again, doing random access, attach into the base station again, receive the downlink connection. And at this point, we would even have to wait for the RRC activity timer again to wait. So this is exactly the situation you would want to avoid if you expect one more package. So it's immediately to use it's important to use the correct flag when you use assist indication. But if you use it correctly, then you can save a lot of energy with it. So these are the two important features for power saving in connected mode. Most of the features, however, are around the idle mode. And the first one is actually idle mode DRX. You could argue whether this should be considered a power saving feature at all, because this is already available in normal communication with plain LTE. So it's just the pulsing of the receiver, so turning it off and on again for some time. So this is what we call paging. So each network has a paging interval, which is set to some amount of time, and only in this interval, when we have these spikes here, the module will even look for incoming data. If it receives some data, then we basically jump back to this stage. So the module wakes up, we do a random access procedure, set up an RSC connection in which it indicates that it has been paged, and then we'll receive the data. And then we go through the stage again. So that's what's idle mode DRX. And the important thing is that we do not have to, that the modules don't have the transceiver on all the time, but just for some small amount of time by a duration which is configured by the network. So the operators are in control of this, and you can basically do nothing about this. And it's important to know how long this is, because this is also some cause for latency, because sometimes a module might miss a paging, and by this data transfer may be slower, or it might take more time until the module reacts to incoming data. Okay, but the next real power saving feature is then enhanced DRX or eDRX. And this basically means that you have windows of inactivity during your idle mode procedures. So on the last picture we saw here that we continuously page for incoming data, so that we have the receiver on and wait for base station to tell us that there's incoming data. With eDRX, we then configure a width, so a paging transmission, a so-called paging transmission window, which defines the time we want to stay in this idle mode and listen for pagings. And then we also define a cycle. So this is when we repeat this window. And in between these windows, there are no, we won't turn on the receiver to listen for incoming data. The whole procedure is synchronized with the network, which means that the base stations will not send any data during or indicate any incoming data during the time between these paging transmission windows. So for use cases where you need some availability, but you can live with the fact that you might have to wait for some time until your module actually notices that there's data, eDRX can be used to just reduce the amount of energy reduced during these pagings. So the next power saving feature after this is then the extended tracking area update. Tracking area updates are basically keep alive of the network. So this means the network is segmented in a lot of tracking areas, which are actually used to page a device. So a device or a module is expected to perform a tracking area update whenever it's going to a different tracking area. And then the network can use this information to page modules in a certain tracking area when there's incoming data. So all the base stations in a tracking area will send out broadcast messages when there's incoming data, and the module will then reply to them. However, this is not only when you have to cross a tracking area that a module has to do a tracking area update, it's also some kind of keep alive. So this means that a module or a terminal has to send data, has to do a tracking area update at a regular period to indicate to the network that it is still available for that it's still available and still connected to the network. Without that, the network would consider the module powered down or lost or whatever, without having done a proper detachment. So, and for this, it would just clear it from the tables. And next time the device wants to communicate with the network, the module would have to reattach to the network. In general, this tracking area update with plain LTE is usually restricted to 186 minutes. So this means a module a device has to have an interaction with the network roughly every 3 hours. Without that, it would be considered lost. So if we now especially look at use cases like NB-IoT, then you can imagine that you often have situations where you want to communicate not that often, so maybe 2 or 3 times a day. So just having to wake up the module, going through these process of doing a random access procedure, connecting to the network, perform the tracking area update again, just to send the keep alive would be a huge drain for the battery. For this reason, it is possible to extend the tracking area update up to some time. And the time you can extend this is basically depends on the network. So by the standard, you can prolong it to up to 413 days, which would mean that the module can stay inactive and for more than a year without having any interaction with the network. However, most operators do not support this. So the usual amount of time which operators support is 310 hours, which is just below 2 weeks. So, and especially when we next see the power saving mode, then this feature makes more sense, because it means that you can just keep your module quiet, having no interaction with the network, and you are still attached. So next time you have you want to communicate with the network, you have not to go through the whole procedure of attaching to the network again, but you can just start by communicating. So in general, it's a good idea to send this value higher than the communication frequency you want to use for your normal data you want to send. So in general, the tracking area update should be configured at a value which is higher than the normal cadence of interaction. Okay, and then the last power saving mode is the actual PSM mode. So PSM is different from the other modes. So as it's also an idle mode feature, and what you configure to do PSM is not the time you are in PSM, but the time you are reachable by eDRX, which you stay in normal idle mode procedures before you then go in PSM. In PSM itself, the module is not reachable anymore. So this means the module has turned the transmitter and receiver completely off, and no data will reach the module. However, you can configure sometime before this power saving mode kicks in that for which you want to page for incoming data. So when you send some data, so you would start again in the connected mode, do your stuff, then wait for the inactivity timer to expire, or do release assist indication to shorten this period. And then you can stay for a configurable amount of time in idle mode before you then drop in PSM, where you have a very low energy consumption. Typical values are there are some few microamps of currents which a module uses there. So this is really not a lot. And I think it's especially this power saving mode which makes this old procedure of turning on and off modules in between transactions obsolete, or makes them not, you don't require them anymore when you have power saving mode available, because the energy with the energy, you need to set up a connection again. So to attach to a network, you can stay in the PSM mode for quite some time. Okay. However, it's important to know that this mode here is just for eDRX. It's a common misconception that you should configure there some amount of time to be able to receive acknowledgements for uplink messages. But in general, this is usually not the case because data is only transferred during connected mode. This means when you send some data here, and then would wait for some response of this, then the response usually will reach the module when it's still in connected mode. Even if the network conditions, if the signal conditions are bad and the transferal of the data is slow and you suffer from high latencies, the base station already has data. The module already is starting to receive it. So the RSC inactivity timer is reset. And even if it takes some time, the acknowledgement for a normal message would be received when you're still in connected mode. And this means that in most cases, you can just skip this period to a very short time, unless you have some long-running operations on the server side, which actually takes some 10 seconds or something more, so that you really need to be paged when you already have dropped out of connected mode. But so this general recommendation of staying in idle mode for, let's say, 30 seconds before dropping to PSM is usually, can usually be avoided, and does just draw my energy. For this timer, which tells us how long we are in idle mode before we fall, or we listen to pagings before we fall into PSM, we can see that these variations of this timer usually have a huge impact depending on the coverage extension level we are in. So this means that especially in good signaling, or when we usually have good signal conditions, like indicated here with a yellow line, then you can save a lot of energy when you just shorten this timer. So going here from 15 to 10 seconds, you can, or even slower, so you can nearly get half a year out of battery lifetime. So this is an important thing. When you are in bad signal conditions, like here with CE level 2, then the line becomes more flat, because in this cases other effects are usually more dominant. And to the end, it's also important to note, you can combine these features basically as you see fit and as it suits your use case. Connected mode, DRX, as I said in the beginning, that's a feature an operator has to support, and the module does have to support it, so there's no user or programmer or developer interaction required for this. But using release assist indication, eDRX or PSM, that's all up to you and can be designed in a way how you can best make use of it. However, it's important that configuring these modes can be different from network to network. So the operator is always in control and defines lower and upper bounds for all these timers and values which you want to use. And also the availability of certain features is also up to the operator. So for this reason, it's very important that you tailor your use case to the network you want to deploy your solution in, and that you do not just measure in one network and then assume that you will have the same situation in another network. So this can easily lead to huge problems. So for instance, another operator might have other limitations on eDRX than the country you are tested in, or the network you're tested in, or the feature might not be supported at all. So this might also be the case. So this is something when it comes to power saving modes, which has to be taken into account in advance. And final word is that there are a lot of features available. So we have seen long periodic tau, or extended power, enhanced DRX, power saving mode, early release assistance. These are all features which which can be configured by you and set up for by the developer. But usually you should use only the features you require. There are some features which only make sense when you have a downlink-centric application. So eDRX, for instance, you don't save any energy when by staying in eDRX. If you do not require to be reachable by the network. So this means if you just send some uplink data, like let's say smart parking or smart metering, especially. So then you should use power save mode instead of eDRX, because your device doesn't need to be reachable by the network. The other case, when you have some use case with access control or general use cases where you use actuators, then it's usually required that you can reach your device at a certain and with a certain delay. In this case, eDRX is better. So this applies to all these all these modes. So you have to look carefully which of them suit your use case and which don't. Okay, and with this, I come to an end and would thank you for your attention, and then hand over to Igor for power classes.
Thank you, Thorsten. Let me switch and present my slides. Okay, Thorsten, can you hear me?
Yes, I can hear you.
Good. So I guess all attendees can hear me as well. My name is Igor Toberg. I'm gonna present today a few slides about power classes for cellular IoT devices, and I hope that you'll get some interesting insights, and you, or at least some of you, will be surprised with the insights, and some of you maybe not. So let's start. A few words about myself. My name is Igor Toberg. I'm a director of product marketing at Sony Semiconductor Israel. I'm also serving as the vice chair at the GSMA 5G IT strategy group, and I'm tightly involved with all power saving and power efficiency related topics, both at GSMA and at Sony. Some of you, or I guess all of you, knows well Sony. Sony is a huge company. It rolls about $80 billion annually. And some of you have heard about the company Altair that has been acquired by Sony 6 years ago. So I'm coming from Altair, and now we are called Sony Semiconductor Israel. So basically, this is the same company that has been established more than 15 years ago, and now it's a part of Sony Corporation. There is still a name of Altair that has been kept, and we decided to keep this name as a brand name for our cellular chipset product line. So in some of the publication, you may have seen Sony, Sony Semiconductor Israel, or Altair. So it's all talking about the same. We are a company developing chipsets for cellular IoT. Okay, I'll pick up the pointer. It would work well now. So some of the applications that we are shipping our chipsets, and as I said, we are focusing on the cellular IoT applications. We are not involved with the broadband applications. We are not involved with the smartphone connectivity. We serve the market that requires the data rates that could be supported by two technologies, LTE-M and NB-IoT. For some of our chipsets, we also have support for the 2G fallback, but the major focus of ours these days is about LTE, LTE-M, and NB-IoT. So some of the applications that we are serving these days with our existing chipset, the point-of-sale devices that has an interesting traction recently moving from the broadband chipsets towards LTE-M. There is agricultural applications that are being served mainly by the NB-IoT chipsets. The healthcare applications that has been using for a while with the Wi-Fi or BLE connectivity, and these days we are seeing some interesting trend that such applications are looking for cellular connectivity, and we support these verticals as well. The smart cities applications, smart parking, smart lighting, so these kind of verticals are being supported as well. Consumer electronics, similar to healthcare in the past, these devices, or even today, has been using Wi-Fi and BLE, but these days we've already having several devices supported by our chipset with LTE-M connectivity by wearable applications. Smart metering devices, I'm talking about all types of metering applications. LTE-M and NB-IoT are both used for gas, water, electricity, and heat management metering applications. And the last vertical is about trackers. And for trackers, it's quite wide definition. So I'm talking about trackers for telematics, for logistics, personal trackers, pets trackers, and so on. So the common thing for most of the applications that you are seeing here is that most of these applications are battery operated, and power consumption is critical. And as Torsten said in the previous presentation, there are multiple techniques that has been designed by the 3GPP and supported by most of the MNOs networks. And using these features, you may able to optimize to the power consumption of your device to fit the battery life as expected by these verticals. And for example, for the smart metering applications, there is a need to support 15 and even 20 years. So all these features covered in previous presentations supposed to be utilized and used in order to achieve the maximum battery life from the battery capacity assigned for this particular device. But in addition for that, there is a parameter that is not typically discussed about the power consumption aspect, and this is the power class. At the LTE, the 3GPP defined several power classes for a different type of radio technologies. So the first power class definition for LTE devices has been defined in release 8, and it defined that all devices that the LTE is supposed to be operated at the 23 dBm maximum transmission power. So this is a typical transmission power for all LTE devices. And again, really say this is the initial release, and it was covering the standard LTE operation. That time we didn't have LTE-M, we didn't have NB-IoT, and there was no need for different power classes. But later on, once the LTE-M and NB-IoT technologies has been introduced in release 13, there has been also a new definition with the new power classes defined for LTE-M and NB-IoT. This is the power class 3 that has been used in the past with the 23 dBm, and the power class 5 with the 20 dBm. And still that time, when the release 13 has been defined, and that's still maintained by today, the default power class for all devices that has been operated at the LTE network is 23 dBm, the power class 3. Later on, with the release 14, there has been another power class defined that enables the device to operate at 14 dBm. And first, this power class has been defined for NB-IoT, but with the release 15, there is also a similar definition with the power class 6 for LTE-M. So basically, if you look at the TS document, this is a release 16 document that covers all power classes that I just mentioned. So we have the power class 3 for multiple bands, we have the power class 5 for multiple bands, and the power class 6. And if you noticed here, there is also some higher transmission power allowed. This is the power class 2 with the 26 dBm that has been also approved for some of the LTE bands, like band 31 at 450 megahertz. And this higher power is actually enables better coverage. So if you'll convert the power, and we will say the higher transmission power we make, the wider coverage we get. On the opposite side, the lower power we transmit, the lower power the device is supposed to consume. And this was actually the main assumption when the 3GPP defined the power classes with the low transmission power, with the power class 5 and power class 6. And this was the main question. Why should we reduce the maximum power? We always want to get a wider coverage, of course, but there are some constraints. If there is a device that using a small capacity battery, or this is a device that is supposed to be operated with the coin cell batteries, a typical 23 dBm device cannot be operated. And this was exactly the reason why the 3GPP has defined lower power classes. So the target was to reduce the power consumption, and as an outcome of it, to provide devices that could use smaller batteries, means the batteries would cost less, and the overall size of such devices is supposed to be smaller, because there would be no need for an external power amplifier. The power amplifier for 20 dBm or for lower transmission powers could be integrated in a chipset. And the big question that we would like to ask now is, indeed, this reduction in the transmission power would bring a longer battery life? Would we indeed get a lower power consumption? So let's take a look at the next slide, where I can explain the pros and cons of 20 dBm versus 23 dBm. So as I said, the intention was to reduce the power and to reduce the current consumption. But when we are talking about 20 dBm versus 23 dBm, so this is 3 dB reduction, so means the signal strength is reduced by half, by 50%. The lower transmission power, the lower coverage we'll get. So this is clear. And this was also the assumption by most of the MNOs. The power class 3 was the mandatory requirement, and most of the MNOs has requested it. And recently we see some slight flexibility with some of the MNOs that allows also 20 dBm operation. And let's try to understand if it's indeed a right direction or not. So the advantage of having the power class 5 device, the 20 dBm device, is, as we said in the previous slide, is slightly lower module cost, or the device cost will be cost lower, because there is an integrated PA, and the batteries that's supposed to be smaller and they cost less. But on the con side, we may experience several issues. So let's start with the first one, the coverage issue. So as we said, we are transmitting half the power. We'll get a device that will not reaching the NOB and supposed to use the retransmissions. The retransmissions means additional power that's supposed to be consumed by the device. So this is the higher power consumption due to the repetitions. The higher consumption of the device is reflected in the shorter battery life. If you're talking on the other aspect of the spectral efficiency, and I elaborate more on the next slide, if the device that initially supposed to transmit 23 dBm and to reach the NOB from the first attempt, and in the 20 dBm case, it's not reaching the NOB, the device supposed to retransmit, we are losing the spectral efficiency. So it's a big concern for the MNOs. The same problem comes with the data rates. The more retransmissions we have, the slower data rate. It's also impacted by the longer latency, and the low transmission power is also impacting the coverage, especially for the underground installations. If I'm talking about smart metering applications, where the devices in some of the cases may be installed in some metal cages or underground, losing the 3 dB coverage is a significant impact. And if I want to explain it from a more scientific way, we have that chart. This is the CDF picture of a typical transmission powers of the devices being used by the networks. And what actually we can see here, there are 5 different use cases. So I would focus only on 3 of them. The first one is the rural use case, the second one is the suburban, and the third one is the urban. I will not speak about the indoor use case because this use case assumes femtocells in the close proximity for the UE, and this is not a use case that we want to cover this discussion. So in most of the cases, we have the devices, let's say this is a tracker application that is traveling from point A to point B, and this tracker could be operated in either rural, suburban, or urban environment. So what we can see in this chart, let's focus first of all in the rural use case. So this is the blue dotted line, this is the rural use case, and what states this chart? That the device that transmits 20 dBm or less, that means the transmission power is higher, is located in the area of 30% of the devices that are located in this area. Means the devices that supposed to transmit higher are having 70% of the population that has been sampled in this chart. What the chart means that 70% of the devices that are being used in the rural environment supposed to transmit more power than 20 dBm. So if the device has been defined to operate at the power class 5, it means at the 20 dBm operation, and the device in the remaining 70% of the cases supposed to transmit more power, but it's just physically not developed or designed to transmit more power, the impact is retransmission of the data. So in 70% of the cases for rural operation scenario, we would expect the device will be transmitting twice or 3 times or even more, depends on the distance from the NB. So this is the more severe case, and this is the rural. If we'll talk about the suburban case, so in this the operation scenario, we would expect that there are more NBs are located nearby the UE, and even in this case, the devices of the 20 dBm max power would operate in 60% of the cases with the repetitions. And if you look at the green line, in this line, we can see that the devices in 50% of the cases will need to retransmit. So this is a study, and I also have a link here, so you can take a look at this link later on and to see more details about this chart. But this is roughly bringing some understanding why the device in most of the cases in the rural use case would consume much more power than using the 20 dBm compared to device that has been defined to transmit at 23 dBm. So to translate the figures we've seen in the previous slide to the power consumption, we can take a look at this chart. So this chart is showing an energy that is being consumed by the device that transmits at 23 dBm transmission power. So I can break it down for 4 major pieces. So we have the 3 pieces. This is the baseband. So this we have the digital modem, we have the receiver, and we have the transceiver part. So let's say that this is a fixed amount of energy that is being used for a device which is sending some amount of data. And let's assume that this is a 23 dBm energy that is being consumed by the power amplifier during the transmission of that amount of data. When we switch from a 23 dBm operation for a 20 dBm operation, we say that the power consumption consumed by the power amplifier supposed to be reduced by half, right? So we said 3 dB less. 3 dB less means 50% lower current. And indeed, if we transmit instead of 23 dBm, we transmit at 20 dBm, so the height of this block is going to be half of that one. So we may assume the power consumption of the device will be less. But what happens in this case when the device need to retransmit? And as we've seen in the previous slide, in 70% of the cases, the device would be retransmitting. So the overall duration of transmitting the same data will be double or tripled or even more. So let's say we are not in the worst case and the device is transmitting only twice. So the overall energy consumed by the modem supposed to be increased by a factor of 2, because the time, it's double time to transmit the same data. And if you look at the upper part of the chart, so we would expect that the energy consumed by the power amplifier will be reduced, but at the end, this is exactly the same energy. So we can multiply the time by the current, and this is going to be the overall energy which is consumed by the device which is transmitting 20 dBm. So if we'll compare this chart with that one, we'll see that the overall energy with a device that transmits 23 dBm is lower compared to the device that transmits 20 dBm. And this is the surprise that we would not expect to get, right? So we were expecting, and this was also the initial assumption, that once a device transmitting low power, the device would consume less. But this is not the case. This is physics. Let's move on to the next slide with an additional example. So we try to visualize the battery life reduction with some typical operation scenario. Let's assume this is a tracker device that most of the time sleeping, and the device wakes up every 12 hours. With each and one of the wake-ups, the device is sending some amount of data. So in this case, I'm talking about 10 kilobytes of data to the cloud, and then the device is going back to sleep. So we can simulate the performance based on the power reduction, or in the other way, we can just increase the MCL. This is the coupling loss of this is the path loss. So to make it easier, so we didn't change the transmission power. We stayed at the same 23 dBm at the beginning, but what we did is actually we increased the coupling loss. So the path loss was increased in the steps of 2 dB. So with for example, with the MCL of 142 dB, we may assume that we are located close to the inode B, and there is no issue. With the 145 dB, we are also in the close proximity to the inode B, and in this case, the device is also transmitting, and we are not seeing any degradation. But if the device is getting in a longer distance from the inode B, so the MCL is getting increased, and this is exactly the same representation as the power reduction, as I mentioned in the previous slides, from 23 dBm for 20 dBm. So this is exactly the same situation that we are having here. In this case, the MCL was simulated with 2 dB steps, not a 3 dB, but it roughly gives you some understanding what exactly an expected battery life in this case. So if we reduce the transmission power, or we increase the MCL by only 2 dB, we should expect for about the 50% battery life that is going to be shortened compared to the previous one. If we increase another 2 dB in the path loss, or again decrease another 2 dB on the transmission power, we'll get another 50% less, and this is going so on for the next MCL increase portion. So this is roughly explaining you that reducing the power, the transmission power, as I said, would initially be assumed as a good point, and you may expect for the power consumption reduction, but in reality, this is not the case. The lower power you transmit, the more retransmissions you have, and the shorter battery life you'll get. If you'll move on to the next slide, I would like to explain the impact of a lower transmission class, or the low transmission power from the two directions. So the first one is from the MNO perspective, and the second one is from the device perspective. So if I'm looking at the MNO view, the MNOs are investing huge amount of money in the spectrum. So they buy the spectrum and they wish to utilize the spectrum with the maximum. What means the maximum? They wish the data will be delivered directly in a single attempt from the device to the eNode B, and then vice versa is going to be delivered from the eNode B back to the device. And this is supposed to be done in a single attempt. If there are some retransmissions, and this is the case with the 20 dBm devices, there are devices that are less spectral efficient, means the retransmissions is affecting the overall spectral efficiency that has been allocated by the MNOs. And this is something that MNOs would like to avoid, because the spectrum costs money, and the MNOs would like to have the maximum outcome from the entire spectrum. So we see that the overall operational cost for 20 dBm device for the MNO is actually cost more than the 23 dBm device operation. And if you look at the other direction from the device perspective, so there is indeed some cost difference between 20 dBm to 23 dBm modules. And if I want to quantify this gap is roughly 5% in the cost of the module. So the 20 dBm module would cost about 5% less than 23 dBm. The 20 dBm device to consume more power than the 20 dBm device in challenging conditions. So we saw that in the rural and also in the urban areas. So the impact of higher current consumption is that if you have two devices, one of the devices will be operated with exactly the same operating scenario using 20 dBm, and the second one will be operating at the 23 dBm using exactly the same batteries. The lifespan for 20 dBm will be shorter than the 23 dBm. So just to summarize the key points here, if you are looking as a developer for to design a product, you should consider the proper power class selection, and our recommendation is going for the 23 dBm, and you have all the advantages and disadvantages mentioned in this presentation. There will be indeed some cost reduction on the module cost, but this is going to be only seen at the short term, while in the longer term, if you look at the overall cost that you may waste on the batteries that are typically cost much more than the 5% gap on the module side, the total cost of ownership for the 20 dBm device will be higher than the device transmitting 23 dBm with the power class 3. And this is my last slide. If you have any questions, please feel free to ask in the chat.
Okay, I will take over from here. Thank you so much to both of you. We have quite a lot of questions, so I will try to be as precise as possible. So I start from the beginning. I guess this is to Thorsten, but please feel free to both of you to answer them. Do you know in average how much power is being consumed for paging? So you mentioned the pagings in the first two sections. You are on mute, sorry, Thorsten.
Yeah, yes, sorry, I just look at these values in amps, so I don't know the values by heart. So it's also very module dependent. Maybe Igor, you have a value in mind, so because I would have to look something up, so which I cannot do immediately.
Yeah, so actually I can recommend a document that has been prepared together with Deutsche Telekom and GSMA. This is the energy efficiency guide. It has been published, and I can take and post here also the link for this document. We did the analysis based on several module vendors based on different chipsets, so you can get in this document also the measured scenarios for different operational modes, including PSM and eDRX and tau release assistance indication and so on. So all this has been measured and explained in this document. So I will post the link here. You can take
we can also we will also provide this recording to the participants, and we can also include this document in the email. If you can send that to me, that also works.
Yeah, sure, I'll do so. So this is a public document by the GSMA, and that's a good one.
I am sure. Okay, moving on with another question. So can the release assistant indicator be used with both NB-IoT and LTE-M? Are there the differences between this property with NB-IoT and LTE-M?
Yeah, it depends on the network generation. So usually release assist indication is only available in NB-IoT. So for LTE-M, so you need higher generations for this. So
Okay.
which means that there are no operating networks I know of which support it yet.
Okay, thank you. I move on. Will the network buffer the downlink data if the device is in the power saving mode?
I should have explained this when I showed the slide. So this happens in PSM and also in eDRX. So when the module is not paging, so the states are synchronized. So the network knows that the module is in PSM, or it knows that's in the inactive part of an eDRX cycle, and then it will buffer the messages. How big the messages may be and how many messages depends on the network operator. But in DT network, we buffer 10 messages up to 1 kilobyte in size. So then they will be delivered once the device is available for pagings again. So I think there was also a question, so how long they will be stored? They will actually be stored until the next time the device is available again. So this means if you're in PSM, until you either transmit data or do a tracking area update.
Okay, thank you. We answered 2 here. Okay, this is about more the literature. The naming is always confusing. Is PSM a kind of power saving mode? I see people often use PSM as a title, including eDRX, TAU, and all the others.
Okay, this can be confusing. So technically, PSM is the power saving mode, which means the deep sleep mode, which makes the module unavailable in idle, in RSC idle. However, it's often mixed in titles in slides, and then power saving features, power saving modes is used synonymously.
Yeah,
but technically it's just PSM for these features, switching off all the pagings during idle mode.
Okay, perfect, thank you. Okay, another one. Is it possible to exit PSM mode executed by the radio module side and asynchronously? For example, the device detects some events and exit PSM to send an uplink message because it's required. So can you just interrupt it?
Yes, you can at any point in time just break out of PSM mode by transmitting data. So this is always possible, but you are not reachable. So depends a little bit on the module, on what you need to do to wake it up. Some modules just look on the serial line for an AT command. Others need a pin to be raised up, but you can always initiate uplink data transmission. So it's up to you how you design your application.
Okay. I hope we can have 5 more minutes. We discussed differently, but a couple of questions left. So in your slides, Thorsten, starting from page 4 and ongoing, you show the graphs of the signal measurements. Which program and hardware did you use for this measure current consumption?
That's an OTIIA's device from Quartex, a Swedish company. So it's small box, you can plug it in by USB-C onto your laptop, and then it's a normal power meter and the software which belongs to it. I think it's also a former Sony company, or at least former Sony employees who built this.
Yeah, that's right.
Thank you. Okay, another question is, can I expect the same power saving timer settings in all networks supported by a roaming SIM?
No, most of these features are GAN features. So that means the radio features. So like eDRX, it needs to be supported by the network you are in. So it's important to have in mind that these features may be different in each and every network you visit. So it's not coupled to a SIM, but to the network you're in.
Yeah. Okay, another question is, the CDF graph about the power UE transmission power, will it be dependent on the network budget settings, the power distribution?
Yeah, so actually there are 2 questions that I'd like to combine the answers. So the second one is there an MNO network that designed to operate with 20 dBm, or they all operated at 23 dBm? So as I said, all MNOs network has been defined and designed to operate at 23 dBm. So this is why I'm saying the device that is operating at 20 dBm would lose the spectrum efficiency of the network that has been defined for something else. It has been defined for 23 dBm. And this is the reason that you see also the CDF graph, that the assumption of 23 dBm is showing 100% of the connections using 23 dBm, and only 30% or 50 or 60, depends on the case, is being served with the 20 dBm device.
Okay, thank you. Another question is about the deep indoor coverage. So in the case of connecting a device in deep indoor condition, the wireless link would have go through indoor and outdoor conditions. What would be your recommendation for deployment to guarantee connection? The simulation tools or the power clusters? Do you have any, like, a rule of thumb for that? Yeah, so it's always better to allow the device to transmit the maximum the device is allowed to, and this is the 23 dBm as a default. You of course may try the 20 dBm, but then you'll get stuck with some of the deep indoor coverage because the device should retransmit. So you will get the connection still, but the closer you're gonna be to the cell edge, or the deeper you're gonna be at the indoor, the more transmission the device is supposed to retransmit, or at the end you may lose the connection. So the recommendation for us from our side is to use the higher power defined by the standard, and this is the 23 dBm. Okay. Okay. So in that case, it makes more sense to use 23 dBm. Okay, changing the topic. So is normal DRX, or not eDRX, also available in non-IoT modules? Do you think DRX is available in most of the operators?
So in LTE it's available. So this means the cycle is just shorter. So usually in NB-IoT, a typical value for pagings in idle mode is, or for DRX is 2.56 seconds. And normal LTE usually have 640 milliseconds. So and sometimes you can even hear this when you do a call. So you get the free sign only when the pagings have been delivered to the other device, and then the module reacts. So this is just the module waiting for a paging, perhaps missing one, setting up the connection. So this 1 or 2 seconds, you sometimes have to wait until the 2 signs is a module reacting to pagings. So that's what all your cellulars or mobiles do. So yes, it's available.
Thank you. And the last question of today is, how much time and power the registered device in PSM mode will usually take to register again when it needs to wake up and perform transmission at the defined interval? So the power consumption in deregistration and registration.
Yeah, I don't. So I don't know the actual value, but it needs the same amount of power it would need if you don't, if you are not in PSM mode. So if you are just in idle. So what you do, so what you save in power is actually to do a complete attachment. So for this reason, we have to be careful how to use the word register. So this is just setting up a connection on the base station. So you are completely attached all the time. So you don't need to do this initial attachment to the network where you set up a security context, go through all the authentication authorization steps. You just set up connection or resume a connection basically. So and that's the same in PSM as in idle mode. That's the huge advantage of using PSM in contrast to turning off the module, that you just have a small baseline in PSM where you waste power, and then you're immediately able to transmit, in contrast to having to set up all the device. So you're usually faster in having your connection, and yeah, you spare this power you require for doing an attachment. So, but I don't know the actual values. So for this, I would have to do a measurement.
Yeah, maybe in the document that Igor mentioned earlier, we can have more information.
I think there are some typical values.
Yeah, like something for rule of thumb. Okay, also we are through with the questions and already over time. I would like to thanks to both of you again, presenting your deep insights on this topic, and thanks everyone for joining this session.
Thank you all.
Thank you all.
Thank you.
Bye-bye.
Then have a great day and see you tomorrow. Bye-bye.
Bye-bye.